them. If we cannot finish all of them, we probably would try to cover some next week as well. And then beyond this, we won't have such accumulation, and then we should be able to cover during the regular sessions. So without further ado, let's start with this week material if you don't have any questions. You have any questions? Okay, no. So maybe we can discuss the questions a little bit later when you guys. Let me go to the second screen. Okay, so now you should be able to see my screen there. Okay, week five is covering the textbook chapter 6. Basic layout of this chapter includes an introduction and probabilistic modeling with discrete systems and modeling component and system reliability, followed by linear regression. And then I want to point out here that for probabilistic modeling with discrete systems or continuous systems is a separate direction of applied mathematics, which is stochastic process. And then in the weekly material, I have some links on the Markov chain and stochastic process serve as an introduction. Note that I just want to point out that you would actually realize that this course is trying to cover a lot of different concepts. Each single chapter is a specific topic, and then in reality, it really serves as an introduction so that you would have the right knowledge to do more research later on when you need the specific technique. Because in many of the programs, of course, it's in the applied mathematics program or operations research programs, each single chapter that we're trying to cover here is actually one separate course. So in other words, we're trying to introduce some key concepts so that hopefully you would be able to pick it up later on when you really need it. Okay, so let's continue. Previously, we have been developing models using proportionality and determining the constants of proportionality, and then which is actually covered by the first two chapters, I believe. In this chapter, we will allow the constants of proportionality to vary in a random fashion rather than to be fixed. So let's take a look at an example for the rental car example. It says that there are two branches that for a specific car rental company, suppose it's denoted by 1 and 2, because you know that there's possibility that you can rent a car from location 1 and then return the car at location 2. So in that case, we would consider we can define 1 and 2 being two locations, and then in stochastic process, we call it state. So in this particular case, we have two states. And then there's a probability that you rent a car at location 1 and return to the same location, which is represented by P. let me see if I can find my highlight here. Okay, so there's a probability that it goes back to P, and then because in this particular system, it only has 2 locations. So apparently we're trying to simplify this problem, right? We are just trying to say that, let's assume there are only two states. And then in this case, if someone has a probability of P to return to the same location, then it has a probability of 1 minus P to return to a different location, return a car to a different location, which is transitioning from 1 to 2 has a probability of 1 minus P. And then if we assume that the probability of someone renting a car at location 2 and return to the same location with a probability of Q, and correspondingly we would say that the probability that this guy is returning the car to location 1 is 1 minus Q, right? So this is rather straightforward. And then now you start thinking, what if we have more states? Yes, we can still consider that. We can consider if we have the state 3, we have state 4, and then the only thing difference would be from 1 to 2 will be 1 minus P in this case, but rather than being 1 to P, the 1 minus P, there's a probability that 1 to 3, 1 to 4, and also 1 to 2 and 1 to 1 itself. And then all the probability of going out from 1 should add up to 1, because it has to go somewhere, either stay at location 1 or go to some other locations, right? So you have to, if you think about this problem, interestingly, let me get a pen so that I can show you what I want to see next. Hold on. Okay, this pen doesn't look like it's working, so let me see. I may get something. So continuing with this example, if you think about it, just this particular example, we can think the problem as it's really just 2 states from 1 and 2, and then if we use matrix to represent it, we would know that 1 to 1 is P, 1 to 2 is 1 minus P, and then correspondingly this will be Q and 1 minus Q. And then with this discrete transition probability, we want to study what's the long-term behavior of the system, meaning that how much percentage of the cars will be staying in location 1, how many percentage of cars will stay in location 2. And then if we think about another example that I want to discuss here, without continuing with the example, if we think about if we want to model a number, I'm going to briefly introduce this concept. If you're really interested in, please do go ahead and review the Markov chain model that I have. in the week 5 material Markov chain. So in Markov chain, we assume that the arrival process is an M process, which is really called Poisson arrival, meaning that the number of customers that actually arrives at a specific checkout counter follows a Poisson distribution, Poisson process, to be precise. And then the second M stands for the service time distribution. The service time at the counter follows exponential distribution. And then the third element of the queue is number of servers. This one stands for just one server. And then if we want to model this problem, we could say that let's define a state. Remember that we just discussed that state, right? Define that state as number of customers in the system. So in this particular case, because it's only one, even though we call it in the system, it's really just at the counter, right? So state we define as number of customers in the system. Then we would say that we could have one customer in the system, two customers in the system, 3, 4, all possibilities, right? And then we have n customers in the system, and then we know if there's one customer coming in, if currently the system has only one customer, and then coming in another, there's a new customer comes into the system, then this arrival process, we can model it as a Poisson process, assume that is lambda being the rate of arrival. And then assume that the current country has 2 customers, and then assume that one of the customer is actually just finishing the service by the checkout counter. Then the system can be modeled being that it will go to 1, right, with a probability departure rate of mu. Let's assuming that that's the exponential distribution of that. And then apparently there's a certain probability that there's no arrival to the system, which is really just 1 minus lambda. Of course, this is really the rate. It's not quite. This is really should be the probability. So that we can represent that probability by this rate. That's something that you can further review the material in the weekly material that I provided there. So correspondingly, we would be able to do very similar thing, and then we would be able to do the same thing for all the states. We will have a transition matrix that we can discuss, right? And then with this particular transition matrix, we can study how many customers in the system on average, or what's the probability that there will be 1 customer in the system. What will be the probability of there will be 20 customers in the system, right? If it turns out that the conclusion is the probability of having 5 customers in the system have 60%, then it essentially says this one checkout counter would be sufficient for the system to handle. What if conclusion is there's probability of having 20 customers in the system have a probability of 60%. Apparently, it would have caused some sort of congestion in the system, right? So you would be thinking about, okay, well, how about we can study MM2Q, we can study MMNQ, and then at the end, we would be able to understand the system behavior. And then last time, specifically, actually, I used very similar example to discuss simulation. So what if we do not know the arrival distribution? We did some observation, we realized that Poisson distribution cannot fit the model, and then you want to fit a specific model to the arrival process, and then you fail to do that. And then you say, I just don't know. In that particular case, you might start thinking about possibilities of using simulation. And then what if another possibility that I discussed last week, if a specific customer decided to switch queues to a different check-on counter, then in that case, you most probably wouldn't be able to you actually could, but the mathematics would becomes really complicated, and then you most probably would choose to use simulation to simulate the system. You want to understand the system performance such as time in the queue, time in the system, time at the service counter, or overall congestion level of the system. So that's a brief introduction of what we're trying to cover here. And then let's continue with the material. So Mohammed was asking if it's possible to give an example of hidden Markov model. It's really not that straightforward that I cannot come up of something on top of my head at the moment, but I can try to get something, and let's try to discuss in our next session. Or if I will see you next week. Let's just discuss in 2 weeks so that everyone will be on the same page after you guys have a chance to review the regular Markov model. And then I can give you some example or some directions on a hidden Markov model in 2 weeks. And then continue with this, and then we can model so continue with this so that once we know this P and 1 minus P, we can model using the two functions to model the actual quantity or cars in the two locations. One would be in Tampa. In this example, one is Tampa, the other one is Orlando. And then in the long run, we can study that approximately 50% of the cars will be in Tampa, and 43 of them will be in Orlando. So another example that we can use a discrete system to study. And then it happened that this is a voting example, and saying that there is tendency that some of the party members would change their vote to different parties. And in this particular example, for example, Republicans continue to stay with voting someone in Republican Party 0.75% of the probability, and then has 0.2% probability to vote an independent member, and 0.05% to vote a Democrat party member. So it's very similar example as the previous one, except that this one has 3 states. And then if you check at the going out probability would be 0.2 plus 0.0. Okay, I need my pointer. So 0.2 plus 0.05, 0.25 plus 0.75 being 1.0. So we can use similarly we see that previous state of in for the next state of in plus 1 is 0.75% probability of previous Rn times this plus 0.2% the DN would, the probability of the DN would go to Republican. So this would plus 0.2 times DN. And then the third one would be this 0.4 times independent of the IN previous state. And then if we continue with similar study, we can get the long-term some sort of equilibrium of the percentage of the Republican and percentage of corresponding independent Democrat voting. And then next section, we discuss that model, component, and system reliability. Happens that it's really not something new. It's something that I assume that you probably actually studied at high school, even though it can become really complicated if the system is complicated. So in this particular case, we want to define the reliability of a component or system is the probability that it will not fail over a specific time period n. Let Ft be the failure rate of a item, component, or system over time. So Ft is a probability distribution, and capitalized Ft is really the probability accumulative distribution, probability distribution, so that Rt is 1 minus capitalized Ft. And then for a series system, reliability of the system is really reliability of individual components multiplied by each other. And then for a parallel system, why do I say this is something not new? Is for high school physics that we studied resistance. Right? Resistance of a parallel system is really the first one plus the second one minus R1 times R2 T. In this case, even though it's reliability of the system instead of the resistance that we studied earlier. Right? I think so. Yeah. Instead of instead of that, right? So and then for series and parallel system, you really need to look at each individual component and then times them together. Given that if the first system and second system is series, and then you have to look at your RS1, it could be parallel inside S1 subset there. And then now we come to discuss linear regression. And then for basic linear regression model, yi equal to axi plus b, and then for I equal to 1, 2, all the way to m data points. And then normal equations we can solve, and then by deriving using the minimize yi minus y hat squared summation of that. I hope that this is not something new for you. Let me write it out. Summation of I equal to 1 to n of yi. Yi is the actual value, and yi hat, which is the estimation, squared. We're trying to minimize this, which is called sum of squares. Sum squares of the errors, right? Because this is the component is really the squared error, and then add them up. And then in order to minimize this function, apparently we have a constraint yi hat equals to, I'm introduced this because we will study linear programming very soon in week 6, which is actually we have to cover it today. Yeah, and then we have an objective function. We call it minimization problem in this case. and then we have some sort of constraint. Usually we write it as s dot t dot, which is subject to y I hat equals to a xi plus b. Apparently, we don't know this a. We don't know this a yet. We don't know this b yet. So we're trying to estimate based on our observation to find the a and b. And then I'm sure you actually come across this problem here or there in general. So let's just try to formalize it a little bit more. So we're trying to fit a linear line so that the error at the specific data points, this difference squared, that's error because this is your actual value and this is your estimated value at the corresponding x here, right? At this corresponding x1. That's why this piece of the difference is really the error, and then which is yi minus yi hat, right? And then you square that, and then you're trying to minimize all the error summed up. So that's the idea. And then if we continue, what we can do is how can we solve this problem? It's for second order derivative. For second quadratic program, you know that in order to find the maximum, you need to take the first order derivative and try to set it to 0, and then take the second order derivative. In this case, you can take a partial derivative to x and to y, and then set them to 0, and then take the second order derivative to check whether it's larger than 0 or less than 0, so that you can confirm whether it's at the maximum value or minimum value, right? I hope this is not too new for you. In order to find the minimum, so essentially we're trying to take the first order derivative and second set to 0, and the second order derivative to find it's really opening up so that you can find the minimum corresponding values of a and b that can make the error, sum of squared error being minimized. And then that equation set that can solve this problem is called normal equations. And then you can solve your a and b based on the normal equations. Correspondingly, you'll find this slope and the intercept. Even though I already introduced this part, but next section, actually, I believe that the optimization part still considered to continue with the discussion that I just discussed here. Let's go later on. When we get there, I'll try to explain that to you as well. And then this is a part, error sum of squares. And then there's since that you can Neil, I'll come to your question rather soon. So this is SSE, which is called as sum of the error sum of the squares, and then total corrected sum of the squares, SST, is that yi, the observed value, minus y bar squared. So if we continue use this example, assume that y bar is really here. Apparently, it's probably not a straight line. It's not parallel to. I'm saying that it's probably not parallel to x-axis. But total sum squared is trying to use each individual value and how far it is to its corresponding average of this corresponding x. So that's total sum squared and regression sum squared, which is SST minus SSE. So if you do some manipulation of those two, you would find it is the I want to talk about SSR here, sum of square of regression. It's really sum of yi hat 1 minus y bar. So that's saying that what's the estimated value at this location and the difference to the y bar. So we're trying to minimize, that's not minimize, that's part, what we call it as regression sum of squares. And then R square is defined as y minus SSE divided by SST. So which is essentially, because we have SST minus SE on the numerator, so that it's really SSR, right? So essentially saying that how much of the variance of the data is being explained by this particular by this particular function. So it's, if you don't know this yet, for R square, what's the definition of R square? Hopefully you would take another look. Generally speaking, for linear regression, the higher R square, meaning it's a better fit. Apparently, we have to pay attention to overfitting problem. If we have 100 variables to explain the relationship, and then we got 99.99 R square, versus you have 10 variables to explain it, you got 92% R square. In that case, you probably choose the second model instead of the first one. So just give you some general thoughts. And then we need to look at the residuals. Residuals is defined as really just the yi estimate minus yi itself. And then for residuals, let's take a look at whether it's actually randomly distributed. If we don't really see the pattern of the residual plots shows randomness, then there is some sort of problem. In this particular case, if there's a fanning shape, meaning that the model itself, as x-axis increases, the model itself cannot explain the model as well, as good as when the x being small. So in this case, we know something's wrong. And then for linear, or in a linear fashion, or in a curve linear residual plots, then we know the model is not well defined. So what we're really looking for the residual plots would be something truly random, meaning in xy space, it can be anywhere, it can be relatively speaking, we don't really see apparent curvature or shape that we saw as discussed in here. And then these are the homeworks for chapter 6, which is homework 5 for this week. So you can choose 3 out of these 4. If the residual plot is random, that means the model is good. Depending on that, it also has a good R square. At least it means the model is well specified. Okay, and then let's go back to Neil's question. Is using linear algebra x bar equal to ATA inverse ATB also a method? It seems easier. Yes, Neil, that's correct, because it's really for linear algebra and linear regression, we can use matrix form to solve the problem, and even though we are not covering here at all. But if you're interested in, you definitely should review that section, how to use matrix to represent linear regression, and how to solve it. It's actually rather simple if you review the example there. Of course, if you have questions, definitely ask me if you want to further discuss. And then that's chapter 6. Let's move along to chapter 7. That's the material for next week. I'll give you some directions so that when you read the chapter, it's not as bad as you experience, hopefully. So just bear with me for 1 minute. I'll get some water and then we can continue from here. Okay, so let's continue with chapter 7, week 6 material, which will be for next week's reading and homework and all the materials. So for chapter 7, it's really trying to hit to the point that we discussed, the linear programming. And then before that, actually, there is an overview of the optimization modeling, discuss what is the linear programming, and what's the relationship with the rest of the other model types. And then in this chapter, we also discuss that how can we get the linear programming using geometric methods to find the solution. And then after that, the chapter discussed how to use algebraic solution to find the solution. And then the third part of the puzzle is for the linear programming is really the simplex method, how we can use matrix row elimination method to find the solution for a linear program. And then the next part is sensitivity analysis. What if we change 1 unit of x? How would that change the objective function? And then what if we change 1 unit of the we have extra resources on the right hand side? What would happen to the objective function? And then followed by the numerical search methods. In chapter 3, we saw some discussion that when we try to fit a model, three criteria for fitting a selected model to a collection of data. It can minimize the sum of the absolute deviations and minimize the largest of the absolute deviations, Chebyshev criterion, or minimize the sum of the square deviations, least square criteria. So I know that for homework 3, we have this second one that we discussed here. Apparently that some of you actually didn't realize the objective function is really trying to minimize the largest of the absolute deviation instead of the regular linear regression model, minimizing the sum of the squared deviations, which is the third criteria. In that case, if you're trying to just to fit a linear model or linear regression model for that particular homework problem, it's really not correct. Even though if you are able to formalize the problem, and if you cannot solve it using the simplex method, that's actually fine, because it shouldn't, that solution algorithm shouldn't come that early in the chapter. But if you formalize the problem in the wrong direction, then it's just not correct. So that's why later, if we did have time to discuss that problem, we can pay another attention to. But on your own, definitely review the section homework 3 solutions for this particular problem. And also, I want to mention here, speak of homework, I want to mention that even though you only finish 3 of those, all the homeworks, some of them like 5, they're really testing on different aspects of all the materials. So if you didn't get a chance or didn't have enough time to finish all the problems, it's definitely beneficial for yourself. At least you can review the solutions, all the solutions, so that you can get a perspective on what's being covered for a specific chapter. And then there's a reason that I select those questions. Hopefully it covers all the major concepts that I consider to be important. And then discuss what is a linear program. And then for a linear program, we're trying to minimize something and subject to certain constraints. And then apparently here, in order to be a linear program, the objective function has to be linear, and then all the constraints have to be linear. And then the chapter further actually discussed some of the nomenclature for optimization, including decision variables. Decision variables is really the variables that we're trying to make a decision on, and then in this case would be a lot of the x's that we defined. And then there's objective function, which is the optimized function, could be minimization problem, could be a maximization problem. And then constraints. It can have multiple constraints, can be larger than equal to, can be equal to, can be less than equal to, can be having some sort of absolute value in the constraint, can have some sort of squared equal to something in the constraints. Of course, if we're talking about linear program, then all the constraints and objective functions have to be linear. And then one more important thing that would be something we call right-hand side, which is denoted as the BI in this subject to equation. This BI is called right-hand side. And then for optimization problems, it can be constrained, can be unconstrained. And for linear program, there is a unique objective function, and objective function is linear, so that decision variable has a power of 1, meaning ax something, or ax plus b, or ax1 plus bx2 plus etc. And then no product of decision variables in the objective or the constraint. If we have x1 times x2, both of the x1 and x2 being decision variables, then it is really no longer a linear program, right? The coefficients of decision variable in the objective function and each constraint are constant, as I just said, a times x1 plus b times x2, etc. And then decision variables are permitted to assume fractional as well as integer values. That would be considered as a linear program. And then there are other types of programs, including multi-objective or goal programs, include nonlinear program, include dynamic program, stochastic program, or integer program, which is also called mixed integer program, also called MIP. Only difference between linear program and integer program is the decision variables are permitted to be only integer values. In other words, if our x decision becomes 0.6, then it's not considered to be a integer program. If we say that because the x that we're considering is really the number of chairs or number of tables that we're trying to manufacture, then it has to be an integer value. Then it becomes a mixed integer program. We will show shortly why integer program, relatively speaking, is harder to solve than linear program shortly. And then there's an example in the textbook. This used the space shuttle cargo. So the problem is saying that suppose that we have certain volume constraints or certain weight constraints, so that if we have all the if item j is taken, then yj is 1, otherwise it would be 0. So it's also, this particular problem is also called knapsack problem. KNACK, no, it's knapsack, KNAPSACK. So it's knapsack problem. That is to say, if I want to go out, assume that I have a bag, I can carry certain pieces of vegetables. I can also carry certain pieces of water, and I can carry some other things as I wish. But every different single item would have some sort of value for myself, right? If I go out hiking, I have to make a decision on how much water I need to bring, how much how many sandwiches that I may need to bring, etc., with the volume and weight constraints of my bag. So that's a perfect example, the same example as this one. So that if I take yi, in this case, if one of the food or one of the drink that I just mentioned, or some sort of fruit, and then I can, but it takes certain space, vj, right? If I take yj, then it takes certain space, vj. If I add all of them up, it cannot exceed the total volume of my bag. And then meanwhile, I don't really, because I'm go out hiking, I need to carry this bag. I don't want to have the bag to be too heavy. Then we can use similar fashion. If the single item weight is wj, then the sum of all of this cannot exceed the weight limit that I want to carry, maybe 10 pounds or 5 pounds, things like that. And then what I really want trying to maximize is, if I take yj, my happiness index cj is really the benefit for myself if I take yj. So if I add all of them up, if I take one, then I add this particular component. If I don't take something, then I don't add that component, right? As a result, my objective is really trying to maximize this. And then this is the classical knapsack problem. And then the book continues with one nonlinear optimization program, even though it's just the introduction, so you can go through there. You're trying to use a piecewise linear function to to approximate the cost function so that the problem becomes a linear program. In other words, if we're trying to minimize without this piecewise linear function to approximate, then each single piece will be a quadratic or polynomial function. Then the object function would see nonlinear elements there. Relatively speaking, it would be harder to solve, even though it's not something that it cannot be solved. But on the other end, it's always good to know that if the approximation is good enough, why not? We can try this sort of approximation and try to solve it using linear program approach. And then now let's look at one linear programming example. Suppose that a carpenter have this problem, and he only have certain lumber, 690 square footage of lumber, and then he knows that he's trying to make tables and chairs. Assume that he can make X1 units of table, and assume that he is planning to make X1 units of table and X2 units of chairs. And then we know that X1 units of tables can sell. Each table can be sold for $25, and then each chair can be sold for $30, for example. I'm making it up here. I don't really remember that X1 and X2, what it stands for, probably chair or tables in that sort. So let's assume that X1 is chair because it looks like this 25 is more reasonable, and then X2 is a table. So that the objective is I want to maximize my profit, which would be $25 times X1 chair plus $30 times X2 tables. And then there are some certain constraints, right? Because each chair, making one chair is taking 20 square foot of the lumber, and then for one table it needs 30 square footage of the lumber. In that case, I say, okay, because I want to X1 unit and X2 unit such and such, so that my total usage of the lumber cannot exceed what's currently available, which is 690 units. And then next constraint is really labor constraint, because I only have 120 units of labor. Suppose in the system I can only hire two workers work for a certain number of hours, so that overall I cannot exceed 120 units of labor. And on the other end, making a chair needs 5 hours of labor, and making a table needs 4 units of labor. In that case, 5x1 plus 4x2 less than or equal to 120 will be the labor constraint. Apparently, we can add some other constraints, such as I don't have a big budget. I need to consider my total budget has to be less than or equal to certain dollar value, right? It could also have some constraints on the time. X1 takes this much time, X2 takes that much time, even though it's very similar to the labor. Of course, we can use time as a dimension to think about the deadline, etc., so that it can be modeled as well into the constraints. And then X1 and X2 have to be non-negative. Both of them are larger than or equal to 0. So if you think about this problem, and then graphically, what we can do here is we know that one constraint is really on the 2D space. It's really a straight line. which is this constraint 1, right? Because we're trying to say that this sum is less than or equal to 690, so that everything that's beneath this line is feasible. We call it feasible being that it could be a possible solution. That's why it's feasible, right? And then look at the second constraint. Because we're using 5x1 plus 4x2 less than or equal to 120, if this is our line, apparently it is, right? Because when x2, x1 is 0, x2 is 30, and then when x2 is 0, x1 is 24. So that's how we define this line, and then it's less than or equal to 120. So anything below this line would be feasible. And then we see that x1 has to be larger than or equal to 0, x2 has to be larger than or equal to 0. That's why the intersection of all the constraints defines the feasible region, which is the shaded area in this particular problem, right? And then if we look at our objective function y equal to 21, if we use a y to define this objective function, then y equal to 21x1 plus 30x2 is really a straight line that's parallel to this dotted line. Can be anywhere, right? And then if we move those lines to get the maximized solution, then we would find that this particular point is our maximum, which is 12 and 15. And then you would realize that for a linear program, the objective function always happens at the vertex. And then don't be surprised if you claim that you studied linear programming. A lot of interview questions will come from here. Why the linear program? First of all, how to define a linear program? Second of all, why the linear program optimal solution always happens on the vertex? One very important aspect is the feasible region is always convex. Hold on, let me get a page. And then people would ask you how to define a convex region. Hopefully you start, probably majority of you haven't studied this yet. But this is one concept in mathematics that's called convex. Because in linear program, all the constraints are linear, that's why the feasible region is always convex. Convex is defined as any linear combination of the 2 points in the region. Any linear combination of those 2 points would be a line in between. Any linear combination of the 2 points 1 and 2 will stay in the region. Think about it. If we have a shape like this point versus this point, if we connect them together, this point will not be in this region anymore, right? So in this case, that's why this is not a convex region. But in this case, in the first example here, it is really convex. Any linear combination of the 2 points in the region will still be in the region, rather than not in the region for the second example. So that's convex. Because of this feature, because of the convex nature of the feasible region, whatever the objective function is, because objective function is linear, that's why it will always happen to be a vertex, to be the optimal solution. Of course, sometimes it happens that you have two optimal solution, when the objective function is parallel to one of the constraints. When would that happen? When that your objective function becomes, in this example, if your objective function is 20x1 plus 30x2, then you know that your objective function would be parallel to this line, and then at the end, it would be optimal solution would be really 2 points rather than 1. That's a snapshot of general idea of linear programming. And then that there is some sort of definition here. If we can, as I said, objective function is really a set of parallel linear lines, and then in this direction, objective function is decreasing, and in this direction, objective function is increasing. And then, as we can see, that we would say that this objective function is maximized at this point and minimized at a different point here. And again, this is the feasible region. Apparently, if the feasible region is not convex, then this problem is much harder to solve, which is not happening at all for linear program, because the feasible region is always convex. And then for algebraic solutions, you can find all intersection points of the constraints. Determine which intersection points, if any, are feasible to obtain the extreme points. Evaluate the objective function at each extreme point. Choose the extreme points with the largest or smallest value for the objective function. Apparently, that means that we have to study all the intersection points. That's why computation complexity is really intersection point enumeration, which comes to the next point that regarding how we have a better way to solve it, which is a simplex method. The essential idea is it's a Tableau format. Place the linear program in a Tableau format as explained later, and then you find an initial extreme point, and then you have an optimality test, feasibility test, and you start pivot. Pivot itself is more introducing some of the variable into the basis, and then excluding some of the variables out of the basis, and then repeat step 3 to 5 until an optimal extreme point is found. Yeah, please go over this example from page 273 to 278. It's very carefully on how to solve linear program using a simplex method. I want to point out that one of the problem, you have to solve it by hand. You cannot solve it by computer for the first linear program that you're trying to solve. Again, solve the first problem by hand, and then for the rest of them, if you have 3 homeworks, if all of them 3 being the using simplex method, first one you have to solve it by hand. The second and third, you can solve it by computer, which shows that you read this particular section, you know what is the simplex method trying to do. And then here we continue with the brief introduction on the sensitivity analysis. The sensitivity of the optimal solution to changes in the coefficients of the objective function. What is the effect of changing the value of the profit for each table, one of the decision variables? And then the other type of sensitivity is changes in the amount of resources available, which is the right-hand side. What is the change of the objective function if one extra resource is available? In economic interpretation is a marginal value. I think, yeah, I need to check this. I think one of them it should be shadow price. And then last time someone actually discussed whether we talk about dual. Apparently we don't have time here to talk about dual program, but we should spend some time, hopefully next week, 2 weeks from now, on the do problem, as well as the hidden Markov model that we brought up today. And then those are 2 types of sensitivity analysis, and then followed by some numeric search method. But this section for 7.6 is really not as important as what we have discussed earlier. Golden section search method is something that I think we probably studied at high school as well. These are the questions for the homework. Again, solve one of the problem by hand using simplex method. Okay, let me check. Okay, we are running out of time. We actually already running out of time, but we still want to continue to discuss some of the homework. Some general comments before I start. Number one, if a problem has 4 parts, 4 sub questions A, B, C, D, you should solve all of them instead of just one of the 1.A. Then you think that serve as one of the problem. No, you have to solve A, B, C, and D. I know some of you actually only solved 1A instead of 1 A, B, C, D. Then I give you another chance to try to finish them up, to finish BCD as well and resubmit. Of course, I have to take some points out as a penalty because that would be otherwise it wouldn't be fair to the rest of the students. And then another comment that I want to make is I'm really looking for not just myself, but in general as a statistician, as an analyst, you really need to comment your solution. If you did some analysis and then at the end you just give me a code, you don't even say that, okay, the solution of this problem is X and X is good or X is bad, Y X is good, etc. You should comment on your solution so that I know you are going through the problem, you're trying to think through the problem. I think it's not only important in our context, but also important in your real world job. In any of the scenario, if you did some sort of analysis, you have to provide certain insights of your analysis instead of just the results of the analysis. Here's the results. That's not the way it should be. And that's number 2 that I want to point out. And then number 3, again, please review the solutions. So let's actually try to go over some of the homework problems. Let's do this. Let's start from homework 4, and then because that's nearer to that's something that you just finished. Hopefully you still remember, and then we can think about. Hopefully we probably finish 4 and 3 today, and then let's see how much we can finish. If not both of them, let's try to at least finish 4. So for homework 4, the first problem, majority of you guys actually finished this problem rather well. I believe that you did. Everyone actually probably got it. So in general, the idea is just simulation. I'm trying to, the algorithm itself is clear. If you just randomly to take points randomly points x and y and then calculate the fxy for the random xi and yi, and then if it's in there, then I try to increment the counter by 1, otherwise leave counter as is, and then calculate pi by 4 times certain counter divided by the total total random draws. This is the code, and then of course you can test on multiple trials and try to plot certain distribution here. Of course, if you only did 1 or 2 or 3, it's also fine. As we can see that here, we want to point out that at a certain trials, the value of the actual value, the simulated value, is very close to the actual pi. And then the second problem is using the middle square method to generate random numbers. And then you probably still remember that essentially using this particular value powered by 2, and then only take the middle part of that and then output it as the next random number. So for this part, why I have the comments there, so I really want to see some comments like the sequence degenerates to 0 very quickly in this particular example. This is really some comments that you want to put in there instead of saying that, okay, this is a graph, that's it, that's the end of the story. No, that's not really something you should do. You should really comment on your analysis of numbers. And then part B, continue, and part 3. Here for part B, you want to touch upon to be degenerate into 0, but it's really appears pretty good until about 380. It really depends on how you define whether it's pretty good or not. For this particular one, we can see that it's pretty good, but in certain situations, 380 and then it started degenerate or started seeing some sort of cycles, then it's not really a good random number generator at all. And then the third part, we see very similar using 3043. It cycles, and then series begins oscillation at the fourth iteration. So that's some comments that I'm looking for, and then comments about the results and comments already about. Right. So this is the second one, and then the third question is regarding the house race. It's also a simulation, and then that because each one has certain odds, so you can construct a number that so that you can construct a set of probability so that you can see in what situation which house would actually win the race, and then you can output after certain races, output how many cases that certain house actually win. So this is a simulation test again, and then that's the results. I think some of you actually made certain point. I believe it was mainly coming from the fact that you probably forgot. It depends on, of course, if you state that you don't really want to add this one to the weights, then it should be okay too. So that's the solution here. And then going to next question, number 4 question. Trying to use again simulation in certain scenario, in many situation, time t between delivery and order quantity is not fixed, and then you have to see that how you can simulate this process, and then that's a solution. And then followed by the last one is a polynomial fit, and then the homework itself is really I mean the solution itself hopefully is self-explanatory, and then you can go through. The majority of you actually did really excellent job, so I don't see any problem there. Just use this as a reference so that you can review the problem that you didn't get a chance to finish, and then you can study the arrival data, you can study the unload data, and then use certain smoothing function, and then that's the solution for this particular homework solution, homework form. So do you have any questions on this? Actually the solution is already on the weekly material for this. So posting the file, RMD file. I'm not posting the RMD file. One of the main reasons is that I don't want the RMD file to be transferred to some other students for later classes. It is in R, but I really hesitate to share the IMD function. But in any case, let me know if you really want to have that code. And then let's do this because it's rather late. I don't want to continue for too long. So the cubic spline. Okay. And then let's do this because I know that homework 1 is rather simple. So let's quickly go through homework 1, and then we can just go from here, and then we'll try to cover more. Let's try to cover more next week. Actually, I'll be around. Hopefully, maybe the first 20 minutes we can cover homework 2 and 3. Hopefully, you guys can make it. If not, I'll post the audio so that you can take a look at homework 2 and 3 as well next week. Yes, next Wednesday, 8 p.m. we will have office hour. I will explain homework 2 and homework 3. And also, if you have other questions, feel free to ask. Yes, same meetup link. Okay, so but in any case, let's continue with homework 1. Let's try to finish this up so that we don't have a lot of left over for the rest of for next week. Okay, so for homework 1, if we take a look at this one, the first question, dynamical system, is rather simple. An plus 1 equals to an plus 0.01 times an minus 1,000, right? A0 being 50,000. And then we can plot that and see that, okay, the annuity will run out of money in month 69, which is less than 0, from positive to negative in that particular month. Again, actually, one more comment that I want to make regarding homework is, again, I encourage you guys to use R instead of using Excel, because as a statistician, as data analyst, we cannot continue to always just use Excel. Then defeats the purpose that you graduate from master's program of data analytics program. So I encourage you definitely solve the problem in R. Of course, if you use Excel, it's acceptable. But if for the whole semester, I always only see Excel or handwritten problems, then I don't think that's a acceptable situation. So going to the next question, page 17, this particular question is asking about the change delta AN versus N. A lot of you guys actually forgot. A lot of you guys actually calculated the delta AN, but was using n times 5 being the x-axis. But the question is really asking about delta an versus n. So if that happens, then you probably won't see this nice linear relationship anymore. And then that's why some of you probably lost some points on this one. And then for next one, part B, we can use a difference equation to solve part B, and then solve the corresponding n k and c. This is predicted distance minus breaking distance. This essentially is a measure of the residuals that we talked about earlier. In this case, we can consider it as random, even though this part is a little bit higher. It depends on how you evaluate the problem, really. Week 4 should be in week 4. Mauricio was asking where did I post the week 4 solutions. I'll check that. It should be in a week 4 material unless I made a mistake yesterday. But that's this question, and the next question is again is the difference relationship, and then we're trying to solve one. All the employees will know this rumor. So interesting problem. Actually, it can be solved by some other methods as well. Hopefully later on we get a chance to discuss this again. And then for the last question of that part is an economics related question. It's somewhat relevant to what we discussed today for the probability as well, right? So it has next period is related to the previous period, and then price is a function of the previous price and the function of the quantity. And then you can use for different scenarios A, B, C, D. There is some sort of relationship that you can draw, and then you can comment on the results that you see. Again, read those, look at the comments, and hope they will help you to further understand the problem. And then with that, that's the homework 1. And then let's continue, go back, and then let me see, where did I put? Unless I missed it, it should not. So. Oh, okay. Apparently I didn't change the available date. So now you should be able to see it. So I want to actually add some comments there. Take away from last week homework. Simulation can be very powerful tool when there is no math modeling available. And then second one is run multiple runs. A big number preferred if there is no computation constraints to get more stable simulation output. Number 3 is more complicated simulation concepts are out there due to the limit of the course. This serves as an introduction to offer you so that you have enough time to read other books when needed. Good news is there's a simulation course actually is offering in the 4th semester every year. So maybe next semester you would be able to have more exposure to simulation as well. So that's all for today that I prepared. If you don't have any other questions, we can just stop here. Again, next week I will be hosting office hours at 8 p.m. on Wednesday, and I will go through homework 2 and homework 3 during that office hour. So if you are interested in, if you have time, please join us. If not, I will post the audio as well. Someone has a question. Can you also discuss about projects in our next meet? Not sure how complex or trivial should the project could be. Okay, I'll do that. I will make notes, and next week we can discuss the project as well. Because next week, I mean 2 weeks from now, because 2 weeks from now it would be week 7. I believe for project we do have something due in I couldn't remember, it's 8 or 10, but it is the time that we can start thinking about this. Okay, thank you. Good night.